Welcome friends to the 25th lecture on module 2, where we will talk about stochastic processes. This is a lecture on module 2, which is focusing on structural reliability on the online course titled Risk and Reliability of Offshore Structures at NPTEL IIT Madras. Now, we already said that to explain the probability of failure or the reliability index, which is converse of the failure, one can always look into the Boolean variables and one can compare the systems with the elements in parallel or the system with the elements in series, and you can assign the Boolean variables to the failure or non-failure state of these elements, and ultimately one can result in probability of failure, which can indirectly give me the reliability index of the given system. Due to several nonlinearities and other inconsistent and variables present in the given system, which leads to lot of uncertainties, it is very essential that one should find out a process by which these uncertainties in terms of qualifying random variables can be addressed. Alternatively, various researchers have identified different processes by which this can be handled. Two of them were using synthetic data simulation, using Monte Carlo simulation, where the random variable data set are generated using a simulation procedure to qualify the data which can be used as an input variable for the reliability analysis. Alternatively, one can also use perturbation methods to do the same, but in the last lectures we understood that the consequences which arise from non-mapping of proper variables which can be input variable to the reliability analysis can lead to a wrong answer for the reliability analysis. Therefore, we understood that certain issues which are random variables in reliability analysis need to be investigated through mechanical modeling. So, we studied the coupling between the mechanical modeling and reliability analysis, what are the different players in the whole game and what are the factors that influence the mechanical coupling, and we also cited an example in the last lecture showing that how the moment rotation characteristics of a hinged joint can be estimated and how the estimate can go wrong if you are not able to do this through experimental investigations. So, in the whole scenario one can easily understand that the variables which are used in reliability analysis unfortunately vary both in space as well as in time. Whereas, when you convert them into stochastical models, one can get rid of the space variation by substituting a vector, which we discussed in the last lectures, and we can make the variable only vary with respect to time. Therefore, now let us look into in detail more about the stochastic process. So, stochastic process is indexed is actually an indexed set. Let us call this set as x of t, which is a time variable. Let us say elements are small x of t and the whole set is x of t, and where t is an element of the period of time within which you are estimating the reliability analysis. So, it is a set of x of t of the random variable which we say as x of t. Now, one need to design or explain or define, one need to define the complete set of random variables x of t on a sample space So, there are two different kinds of variables which are involved in this process. One is what we call the stochastic variable, which is indicated as x of t in our discussion. It is also called as index. The variable t is also called as index. The index set t, because you know index set t, why? Because t is an element of t. The index set t is typically chosen in a time interval. But interestingly, this has a definite set, because the upper bound of the choice is fixed. So, it has got a definite set. Therefore, if you look at the probabilistic structure of the stochastic process, so the probabilistic structure of stochastic process is described in a similar way as that of random vectors. This is due to the reason that they assume any value within a given set, index set t, and of course, the assumed value or the set is a definite set. Therefore, the stochastic process description is similar to as that of a random variable in probabilistic point of view. Now, if the index set is a definite set, or if the index set is a finite set, then the stochastic process forms a random vector. Interestingly friends, the fact that a stochastic process is a set of random variables makes it natural to describe its probabilistic structure in a way similar to that of random vectors. But in this case, the only difference is the index set, what you explain in stochastic process, is a finite set. Please pay attention to the figure shown on the screen now. The figure shows realization of a stochastic variable, where the variables are x t 1, x t 2 and so on at t 1 and t 2. For example, for a given set of t, index value of t, let us select two values arbitrarily t 1 and t 2. I can call that value as x t 1 and I can call these respective values as x t 2, which are assumed by the sample in the interval of 0 to t, where I am talking about capital T as the index set. So, interestingly, these variables are similar to random vector, because they can assume any value between the index set t, but in the probabilistic angle, the only advantage of a stochastic process or a stochastic variable is other than the random variable in comparison is that they have a finite set of values. Okay? That is very important, and that is where the problem becomes much more simpler when you handle the whole exercise using a stochastic variable instead of a random vector. Please pay attention to the figure shown on the screen again. The figure shows realization and the corresponding probability density function of a specific variable. Now, from the picture what we had in the last screen, which is shown now, let us pick up one set of variable which is x t 1. So, for x t 1 one can easily find out the approximate or appropriate probability density function f x x minus t 1, where we are talking about a specific variable whose values have finite set within a given index time capital T. So, therefore, for a fixed sample space, which is usually the case in reliability analysis of offshore structures, the outcome of stochastic variables the outcome of the set of stochastic variables form an ordinary function which is called realization function. Now, choosing this variable, let us say x 1 of t, choosing this variable within interval of t as an index set is repeated. Then the new realizations will not be same as that of the one what is on the figure. So, then the new realizations will not be same as the earlier one. So, in that way the stochastic process or the stochastic variable also qualifies to be a random variable. Interestingly, the probabilistic content of this variable will remain same. The realization will be different. The realization will be different when you repeat the experiment, but the probabilistic contents of the stochastic process or the stochastic variable will be the same. Okay. So, considering this statement or considering this property, one can say the joint distribution function which is f x of x 1 x 2, which is going to be in the interval of t 1 t 2, can be defined as f x x 1 x 2 t 1 t 2 can be simply said as probability of x t 1 less than or equal to x 1 intersection x t 2 less than or equal to x 2. So, let us see equation number 1. So, the joint distribution function as given by equation 1 for arbitrary interval t 1 t 2 which is element of t square is called the joint distribution function of order 2. The corresponding joint density function is given by, let us say, f x x 1 x 2 t 1 t 2 is going to be dou f x x 1 x 2 t 1 t 2 by dou x 1 dou x 2. Let me call this equation number 2. Therefore, friends, in describing a stochastic process, following functions of time are important. So, following functions of time are important in describing the stochastic process. The mean value of the function, let us say, mean value function which we call mu x of t is defined as an expected value of x of t is given by is the expected value of x of t, which is minus to plus infinity x f of x of x and t of dx. Equation number 3. Now, the autocorrelation function between the arbitrary interval chosen, which is r x x t 1 t 2, it will be equal to the joint moment of the random variables x of t 1 and x of t 2, which can be given by question 4. The autocovariance function which is Cxx t1 t2 is the covariance of the random variables x t1 and x t2 and is given by let us say C x x t1 t2 is expected value of x t1 minus mu x t1 x t2 minus mu x t2 which can be r x x t1 t2 minus mu t1 t2. Let us say equation 5. Now, by setting t2 t1 as t, the variance function which is sigma x square of t of the random variable x of t is given by the variance of the variable is the autocovariance function, which is now going to be t comma t, because I am now setting t1 t2 as t and we already have an expression for autocovariance t1 and t2 given by equation 5. I am just reproducing them slightly in a different manner, because this is now equal to r x of t1 t2. Therefore, I simply say r x x of t comma t minus mu x of t1 mu x of t2, I simply say mu x of t square. So, equation number 6. The autocorrelation coefficient in this case which is indicated as rho x x t comma t. Okay, let us say t1 comma t2, let us write the general expression, is defined as rho x x t1 t2 is given by C x x t1 t2 divided by sigma x of t 1 sigma x of t 2, equation number 7. Now, friends, for an important group of stochastic processes, all finite dimensional distributions are invariant to the linear translation of the index set. So, if you have a property of this order, that is, if the finite dimension distributions are invariant to a linear translation of the index set T, then this process is called strictly homogeneous. Such process has great advantage in the reliability analysis. Now, further, if the index parameter is time, as in this case, then they are also called stationary. We all know in probability and statistics, the stationary processes have lot of advantage in handling them with probabilistic tools. When this invariant assumption holds good only for distributions of order 1 or 2, when this invariant assumption, because now we said it is a general one, it is available as invariant to linear transformation for the entire subset of T, but unfortunately or incidentally, if this invariant relationship is valid only up to, let us say, a certain order of T, say 1 or 2, let us say, then the process is called weakly homogeneous. Further, if the index is time, and is valid only for lower orders of index T, then it is called weakly stationary. Now, what would be the consequence if I have a stochastic process which is either weakly homogeneous or strictly homogeneous, or on the other hand, if my process is indexing time, then if it becomes weakly homogeneous or weakly stationary, what would be the consequence? Now, one can look at an important consequence which arises from this. An important consequence of the assumption of the stationarity is f of x x t okay, x t and f of x x t becomes independent of t. So that we can omit in the whole analysis reference to t. So, if this is the case, one can omit the reference to t in the analysis. If we talk about second order distributions, let us say second order distributions will only depend on the difference of index parameter tau. Which can be the difference between the intervals t1 and t2 chosen within the index time t. Now, this statement is true for all other statistics. Therefore, friends, in practical applications, modeling of physical quantity by a stochastic process is based on a very important statement. So, in physical quantity, if you want to model the quantity by a stochastic process, then it is based on an important statement that it depends on single realization of a stationary process. If only one realization is at hand, then the mean value is very easy. So, if there is only one realization, then the mean value is given by the subset or the space set t 0 to t x of tau d tau, let us say equation 8. Therefore, equation 8 simply shows us it is a time average process. So, if this time average approaches a condition mu x for t greater than infinity, then the process, let us say t tends to infinity, not greater, tends to infinity, then the process becomes ergodic. In the mean value. In the same manner, a process is ergodic in correlation if the following condition is satisfied. That is R of tau 1 by t minus tau 0 to t minus tau x of t plus tau x of tau d tau dt. Call equation number 9. Now, if the above value approaches R x x of tau for t tending towards infinity, then the process can be called as ergodic. Interestingly, in the whole explanation, the stationary property is an assumption behind the definition of an ergodic process. That is important. The stationary property is an assumption behind the ergodic process. So that any ergodic process is stationary, but not vice versa. So, very important statement. Any ergodic process is stationary, but not vice versa. That is important. Now, let us apply this concept of understanding to a Gaussian process. A process which is x of t and t is an index time capital T is said to be Gaussian if the random variables x at t1, x at t2, so on, x at tn are jointly normal for any n. Any n t1, t2 chosen within index capital T. Therefore, I can write f of x of x1 xn t1 t2 tn is given by 1 by 2 pi to the power of n by 2 c to the power of half e to the power of minus half summation of I comma j equals 1 to n of x I minus mu x at T I m I j x j minus mu x T j. Equation 10, where C bar is the autocovariance matrix. So, C bar is actually given by a matrix which can be C x x T 1 T 2 varying from and extending till C x x T n T 1. Similarly, C x x varying T 1 T n, of course, this is going to be T 1 T 1, okay, and this varies and extends as C x x T n T n. So, that is going to be the autocovariance matrix which is used in equation 10. I will call this as equation 11, and in the equation 10 m I j is the ith jth element in C minus 1. So, it is very clear from the definition that a Gaussian process is completely determined by the mean value. So, one can say a Gaussian process is completely determined by the mean value function which can be said as mu x of t, and autocovariance function which is given by C x x interval t 1 and t 2. Therefore, interestingly, a stationary Gaussian process is always strictly stationary. Okay. It cannot be weakly stationary at all. So, friends, in this lecture we introduce you about the stochastic process, what is a stochastic variable, how a stochastic variable compares with a random variable, and what are those statistical properties in terms of autocovariance function, cross correlation coefficients, how they can be derived for a given process of stochastic variables within interval t 1 t 2 in a subset of index t. In the process we also explain what do you mean by ergodic, stationary, and ultimately we fixed up a specific case of a Gaussian process and showed that Gaussian process, if it is stationary, will remain as strictly stationary and not at all weakly stationary. Thank you very much.